All right, so in Chapter 6, we're going to tie together our polynomials and our fields and rings that we were discussing before that. So we're going to talk about a particular kind of field, a field generated by an element. So our setup, we're going to recall a couple of definitions before we get started. So we have K over F, a field extension. A is some element in K. And we defined these two objects earlier in the course. So F adjoin A with the square brackets was the smallest ring that contained both F and little a. So it was a ring in between F and K. F was a small field, K is the big field. F adjoin A is a ring in between the two. It contains both the whole field F along with A, and it's this set of polynomials in A, it's sometimes called. So we're using, they're sort of structured like polynomials, but with A in place of a variable. So this element from K in place of a variable. All right. And then we added a new layer to this, which was let's take that ring and turn it into a field by allowing denominators, allowing these multiplicative inverses. So this guy is the smallest field that contains F and A. It's the smallest field containing F and A. And it just has these denominators. Sometimes it's called rational functions in A. And that functions in A, that rational means we're allowing denominators. Okay, so what we want to do is compare these two, and I think that I've alluded to this before, but our main question is when are these the same thing? So when is the ring really a field? So when does F adjoin A as the ring equal F adjoin A as the field? And we know that this happens sometimes with like Q adjoin root 2 was actually a field without needing to add denominators because we had the denominators already. We knew how to rationalize those denominators. So the idea here, the first one up there, the polynomials in A are much easier to deal with. It's easier to not think about denominators, so when can we get away with that? All right, so it turns out what's going to be important is that concept of algebraic. So it's the concept of A being algebraic over F. So our goal here is going to be to prove that F adjoin A as a ring is actually already a field if and only if A is algebraic over F. Okay, and I left a little space there because I remind you also about what algebraic meant. So algebraic over F meant it was the root of a polynomial. And so we can write that down write down for some f of x polynomial that looks like f0 plus f1x dot 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 all the way up to fn x to the n. For that polynomial, when I plug in a, I get 0 out. Another way to write that down is that I can do f0 plus f1a plus f2a squared dot 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 up to fn a to the n is equal to 0. And both of those ways of thinking about it are going to be useful to us. All right, let's see if we can do a part of this theorem. So that theorem at the bottom, that the ring actually is a field if and only if A is algebraic over F. Turns out that, so this is a two-direction theorem, right? It says if the ring is a field, then A is algebraic, and it says if A is algebraic, then the ring is a field. Turns out that one direction is pretty easy and the other one is going to be harder. So here's the easy direction. If the ring is already a field, then A is algebraic over F, and we can prove this pretty easily. So here is our proof. We're going to start by saying suppose FA is a field. Okay, so then what that means is, in particular, 1 over A is in F adjoin A as a ring. So for some coefficients, F0, F1, dot, 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 up to Fn, in F, 1 over A is equal to F0 plus F1A plus F2A squared plus dot, 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 all the way up to Fn, A to the n. Okay, so if 1 over A is in F adjoin A, the ring, then it means we can write 1 over A as one of those polynomial expressions in A. Okay, so now I'm going to multiply both sides by A. So then that means that 1 is F0A plus F1A squared, F2A cubed, up to Fn, A to the n plus 1. And now I'm going to subtract from both sides. So I get negative 1 plus F0A plus F1A squared, dot, 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 up to Fn, A to the n plus 1 is equal to 0. And now that should be looking a little bit familiar. We have this expression with coefficients f and powers of a equal to 0. So I'm going to be extra explicit and say this means that a is the root of the polynomial f of x equals, and I'm going to actually write that in the line below so I have plenty of space. F of x is the constant term for the polynomial is minus 1. Then we have f0x, f1x squared, f2x cubed, all the way up to fn x to the n plus 1. And so saying a is the root of a polynomial means that a is algebraic over the field of coefficients, so over the field f, because all of those coefficients were in f. All right, so that's one direction of our proof, our if and only if proof. That's our goal for this chapter. It turns out the other direction is harder. So the other direction, which says if A is algebraic, then F adjoin A is a field, is harder to do. And in order to do that, we need a little bit more machinery, so we'll introduce that in the next videos.